Hey everyone. So today is going to be our last science video or two. And before I get started, I just wanted to say thank you to all of you for your attention and your interest that you guys have developed in science this year. It was really a pleasure being your science teacher last year and this school year. As of right now, I don't know the marks of your science tests because I'm not in charge of marking them. So as of right now, like as of the filming of this video, I have no idea how you guys did, but I'm sure you guys did well. Based on how the Flamingos math exam went last week, I have faith that you guys all studied the same way and got yourselves, into gear for this exam. So I'm looking forward to seeing how you guys did, but I'm sure you guys did really well. So what I was thinking we'll do just kind of as a last video, obviously you don't have to take any notes, you don't have to write this down, you don't have to remember this if you don't want to, but I just thought, what's an interesting topic that it's sort of come up in conversation in science class, but we never really talked about it. And so what I decided on was gravity. Now, we've talked about gravity a little bit, but what I was thinking I'll do is sort of show in perhaps a little bit more detail how you can sort of picture gravity to work. All right, so basically, the way this goes is start with, a person. We've got one of you, you guys can pick whoever you want, to be standing on a surface. All right, now this surface is not a rigid, solid surface like the ground, but it's more like a trampoline or something, something like that, that if you put any weight on it, it dips downwards. All right, so something like this. This is the sort of a basic idea of how Einstein envisioned gravity to work. So the way Newton pictured it was that it's a force that's pulling on other things, right? That you have this marker suspended above the ground, and the entire Earth is pulling this marker to the ground. Einstein said that it doesn't really work that way. He says that it works more like this kind of thing. And if you look at this, if you're standing on a trampoline, and let's say someone places a ball right there on the trampoline next to you, you wouldn't say that you magically pulled this ball to you by causing it to roll down the trampoline until it hits you, right? That most people probably would say that, it rolled down because the trampoline was curved, so it just, it rolled down the curve because if you have a slope and a ball on it, the ball rolls down the slope, right? That's we see that every day. So this is not anything new or scary or anything like that. But basically the idea of gravity that we had before was that the reason for this motion was some force. And basically what Einstein did is he came along and said there's no such force at play here. It's all just geometry, shapes and properties of those shapes. So basically let's replace this trampoline with, instead of it being a trampoline, call it space-time. So basically, instead of a trampoline, that surface, that fabric, is now basically the fabric of, the universe. And instead of you in the middle, we'll put something much, much larger and heavier like the sun. All right, so we've got, a star in there. All right, something like that. That's not a very spherical star, but don't worry about it. So, I think that's even worse. There we go. So we've got a star, you could call it the sun, call it whatever, but basically we've got a star here, and what it does is it curves this fabric underneath it. Now that fabric is said to be the fabric of space-time, not the fabric of space, not the fabric of time, but both of them together. So basically, if you're messing around with space, you're also messing around with time. And we've talked about this a little bit, that if you are in the presence of an object that has a really, really strong gravitational pull, like a planet or a star or a black hole, that time on your watch will actually tick more slowly than if you were farther away. And that's basically that if you're in this kind of a region where you've distorted space a lot by the presence of this heavy object in the middle, then you've also distorted time in that region. And so that's sort of the basic idea behind space-time, is that if you mess with one, you're messing with the other. The two of them are connected. Your speed in the universe is split between how fast you're traveling through space and how fast you're traveling through time. So if you're not traveling very much through space, then you're traveling through time at about as fast as you would ever perceive it to be. But if you're traveling really fast in space, then you're not traveling very fast in time, thereby meaning that your clock slows down because you're traveling slower in time than you normally would be. So it's a little bit confusing to think about it, but that's basically the way it works, hopefully. So we've got this star in the middle. Now, if you do the same thing that we did before and you take a planet and you put a planet there, now if you just drop a planet there, it's going to do the exact same thing as the trampoline and roll down right until it collides with the star, right? Now, obviously, in space is three-dimensional, so you wouldn't see it roll downwards, because in this concept, the way I've drawn this is suggesting that even this star and this planet are being pulled downwards by some gravitational force. It works kind of differently in 3 dimensions, but it's really hard to draw it in 3 dimensions. So basically you can picture it that it's like it's warping space in this direction caused by its mass. In 3 dimensions you'd have to draw it more like a grid, so like with nothing around, if you had just empty space with nothing around it, it would just be a nice, perfect, neat little grid. But if you've got a massive object like a star, then that grid gets all curved and distorted, but it gets curved and distorted in every direction. So it would look something like this. I mean, this isn't a perfect representation by any means, but basically you have this grid that's basically still the fabric of space-time is just getting warped in all directions. And so if you draw it as a grid, then perhaps it becomes a little bit easier to see that. But something like that. So basically you've got that it's getting warped in every direction. And you can also sort of picture that from the front, if you were drawing lines outside of the whiteboard going this way, that those lines would also be bent and twisted here, and same thing for lines coming from behind the board would be bent and twisted by the star. So in 3 dimensions, you can also almost picture it like if you had a grid that's sort of like if it's, if you've got this 3-dimensional grid, like if you just have like a cube that's made out of toothpicks or something, then basically you have this grid sort of idea going on in the back. So you've got this kind of mess of just these grid lines, but they all distort and twist at the same time. So it looks like this grid, for any of you who have looked at the Cartesian plane before, if you haven't, don't worry about it, but if you've looked at the Cartesian plane before, then you can sort of picture it as those grid lines all just sort of tightening into the same spot. And so if you expand that to 3 dimensions, obviously it's a little bit difficult when you've only been working in 2 dimensions to try and picture it in 3, but if you can picture it in 3, it's almost like all of space-time is getting sort of sucked in towards a point. It's sort of how it looks if you try to visualize it. That's not the most accurate representation of it, but if you're trying to draw this as precisely as you can, you have 3 dimensions of space and 1 dimension of time. And I don't know about you, but I don't know how to draw things in 4 dimensions, so you'll have to use your imagination a little bit, or look up some YouTube videos where people have used programs or real life demonstrations to try and show it. So basically this is what we've got. We've got this star and this planet, and if we ignore the fact that we've created this dip here. So the planet wouldn't roll down necessarily, because you wouldn't see that in space. It would be a little bit weird if you had a star and a planet, and the planet just moves in this wiggly line towards the star. You would expect naturally that the planet would fall directly into the star, right, in a straight path, which is a lot easier to see if you picture it in the sense of your star is down here and your planet is up here, and the star's gravity pulls the planet down. That's more like what we see. If you drop a ball onto another ball, this is the path that it would take, right? And that's basically what it looks like on a larger scale, except that motion is caused by the mass of the bigger ball. So basically what happens here is if you just drop this planet here without any speed to it, it'll just fall into the star in the center, which is kind of a fiery death, and we don't really want that. So what you do is you give this planet a velocity. You kind of flick it. As you place it there, you flick it so that its motion takes it, like, I don't know how to draw this, but its motion takes it out like horizontally. I don't know if you can sort of see what I'm trying to do. That you flick it so that it's moving this way, out of the board, and then but this curvature of the star will also be the same in 3 dimensions. So if you were to look at this star out of the board, the space-time around it would have that same wavy pattern. So even once the planet goes from here to out here, that wavy curve of the gravitational pull of the star is still there. So the planet, basically what it does is along its entire path, it's got the star somewhere over in this direction, the planet is somewhere here, but this wavy pattern of space and what the space-time around the planet looks like is always the same. Now, if you have this sort of like a track, like if you had like a racetrack that was curved in this way, and it was curved in a circular path, the easiest thing for you to do would be to just follow that curve, right? You can picture it sort of like the swing down in the new classroom, where, I don't know if it's operational again. Last I saw it wasn't, but before that, what some of you were doing was you saw that the swing in its setup, it's got that ring, but then inside that the net itself was bent downwards. It sort of created the same dip that we saw here. And what I saw some of you trying to do a couple of times was you would take one of the yellow soccer balls and try and roll it onto the swing such that it went around and around in a circle. And that's basically what is happening with this planet here. If you give it that speed to start, to get it going, the idea is that it'll just follow that curve, the same way it would follow the curve of the swing. That if you took one of those footballs and you put it here and you flicked it so that it's moving like in a direction perpendicular to the center of the swing, then it'll move in this kind of trajectory. It'll go all the way around and come back to where it started. And if it's moving fast enough, then it should keep doing that forever. Now, in our demonstrations with the swing, your guys playing around with the ball and the swing, it didn't work out forever, but that's because, there's like friction between the ball and the swing, and there's air resistance and all these things that cause it to lose a little bit of energy, a little bit of momentum, and then it slows down until it falls into the middle. Which, the falling into the middle is basically what would have happened if you didn't give it that original speed going away from the middle, like going in a direction perpendicular to the middle. So, basically it's the same thing with a planet. If this curving of space-time goes around in a whole circle around the star, that's basically like the swing. And the thing that the planet does is if it has that horizontal motion, then it'll just follow those curves and continue traveling around the star. If that planet happens to collide with something else that removes its horizontal motion, then it would just fall into the star. But that's an occurrence that's extremely, extremely rare and unlikely, because it would need to be a collision that makes it come to a dead stop, which is really, really hard to get. But yeah, so basically this is the idea that we have with space and time, and how they're linked together is through this sort of curvature. So this planet, because it's, responding to that curvature, means it's in the gravitational field of that star, and in a fairly strong one because you can see that curve. If you had a completely empty universe, so all the space is flat, and then you put an object in the middle, in this divot, then it's not that this object has it only goes up to here, and anything beyond that won't be attracted to this object, and the same on the other side. It doesn't work that way. Basically what happens is this object now distorts all of space all the way to the edges of the universe. Out here it's effectively nothing. Like if you put another object there, it would take an eternity for it to actually reach this ball, because its acceleration would be so slow due to gravity that it's going to take, millions or billions of years to get here, just because it's moving so slowly. But the idea is that every object with mass gravitationally attracts every other object with mass. And so, and really just basically distorts space everywhere by a little bit. And then in some regions close to where that object is, it distorts space a lot more, like you can see with the star and the planet here. So this planet definitely obeys, this circular motion around the star, but it's the same thing for an object that's over here. The gravitational field isn't as pronounced, so it moves more slowly. It can take a bigger orbit, but it will still go behind the star and then around the star and back to where it started, and it'll create its own orbit that way. Same thing for this one. Because of its horizontal motion, it'll go around the star this way and then behind the star and come back to where it started. So that's sort of how you can try to picture gravity. There are some really good documentaries that kind of visualize sort of what's going on here. If you're interested, you can look up Brian Greene. He's my favorite physicist, and he has a series called The Elegant Universe, and in that he has a lot of these sort of visual representations of how space and time work. The Elegant Universe. So I'll leave that there in case anyone wants to write that down and check it out. Obviously, you guys have summer starting in like a couple days, so I get it if you're not particularly excited by this, but if you want to know more, then you can look up that. He's got like it's a several part sort of series. They don't all have the same title, but they're all made in the same format, so I just kind of lump them together. But they're all like 50-minute documentaries or hour-long documentaries that you can check out if you want to see more on this kind of thing. But so basically, this is the idea that we've got for gravity, and if you change the mass of the object, then you change how much it affects space-time, basically. So let me erase this because this is getting kind of hard to follow. So let's say you've got your star here, and then you've got a planet there. All right, so if we draw the gravitational field, if we draw this curvature of space-time according to the sun, like caused by the sun's mass, then it might look something like this on that side, and like this on the other side. But I said everything with mass will affect this, the geometry of space-time, the shape of space-time. So that means that this planet also has to distort space-time just a little bit. So this planet will actually also cause space-time to dip just a little bit around it. And what this allows the planet to do is, if it has another smaller object, like a moon, that moon will follow the curves in the planet's path, and then the planet itself with the moon follows the curves in the star's path. So if I draw this a little bit, maybe I'll draw the planet and moon a little bit closer to the star, so you can kind of see what I mean. So if I draw the planet here, you can see that the space-time is still on a slant there, that if you just had a ball on a trampoline, that this ball would definitely roll down towards the star, because the ground here is a little bit sloped. So you can understand that the planet would go around the star, but the planet also modifies the shape of space-time just a little bit. So if we just change that a bit, so we put a planet there, that's kind of an egg, but don't worry about it. And then you put a moon here. We've already sort of established that the planet is going around the star, so that's a given. But you can see from here with this moon, it's kind of on the way I've drawn it, it's sort of on the peak of this little hill between the dip towards the sun and the dip towards the planet. But if I just move this over a little, I'm going to make the planet smaller as well. So the planet's there, okay, and then we've got this hill, and then it dips down towards the star. If you put the moon on the close enough to the planet, the dip towards the planet is stronger than the dip towards the sun. The dip towards the sun is on the other side of this peak. Basically, we've got this little hill peak, and the moon is sitting right here with the planet in that direction and the star in that direction. So even though the star has a stronger gravitational pull and affects space-time more, locally, that is, in this little region of space, the planet affects space-time more than the star. So the moon falls into orbit around the planet instead. And then that planet, as we established, falls into orbit around the star. And so that's how you could get these progressively smaller and smaller systems. If you take this system and you expand it outwards, you could consider this to be a star, and you could consider this to be a galaxy or a larger star, or the center of the Milky Way galaxy, like a Sagittarius A star, the supermassive black hole at the center of the galaxy, would warp space-time a lot because black holes are really heavy. So you can expand this outwards. You can also consider this on an even smaller scale, that if this was the Earth, this was the moon, this was a satellite, then you can have a satellite in orbit around the moon in orbit around the Earth in orbit around the sun in orbit around Sagittarius A star, and so on. As you can keep extrapolating this idea of smaller things obeying these curves around bigger things applies everywhere. Now, this model of gravity does kind of break down when you try to make the math of all of this agree with the math of quantum mechanics. So there's still something that physicists need to figure out, which is how to make this math, which is general relativity, how to make the math of general relativity agree with the math of quantum mechanics, because when they try to put the two together right now, all the answers break down and don't make sense. So there's still something that needs to be figured out there. But basically, this is the way space-time works, but we haven't really talked about, gravity's most extreme beast, which is a black hole. Right now, a black hole is incredibly small and has a really, really large mass. So let's kind of build our way up to it. If we've got a person here, people are small, okay. So if I draw this to scale, then the person should be like, that big. And this person would affect space-time just a little bit in a tiny region of space, and then not very much outside of that. If you can see, the space-time has dipped just a little bit around where this person is. Now if you have like a moon or a planet or a star, obviously space-time is affected much more significantly by an object like this. But for a black hole, it could be, the size of a person or smaller, depending on the black hole, but contain the mass of something much, much heavier. So if you take a black hole compared to this star, the black hole might only be this big, but it might contain the mass of 1,000,000 of these stars. So basically, the dip is going to be extremely, extremely sharp for the black hole. So if the black hole is only that big, well then the dip caused by its gravitational pull is going to be an extreme one, because it has to drop significantly just to a very small region of space. So here's your black hole, but it's got such a strong gravitational pull that if you had a star that was equivalent to its mass, basically if you had a star with the same mass as that black hole, then yeah, sure, it'll warp space-time a lot, but over a huge region. So the steepness of this won't be as severe as for a black hole. The dip might be the same at its lowest point. I haven't drawn it very well, but the dip at its lowest point might be the same or very similar to the black hole, but it's over such a huge region of space that this is not anything to worry about. If you had a person standing on a hill, they don't need any like mountain climbing, rock climbing equipment to go up this hill. Everybody runs up hills like these all the time. It's no problem. So replace the person with a photon, and the photon has no trouble escaping from the star. The star emits a photon, and the photon has no problem with running up this hill and just leaving the star forever. But if you put a person on a cliff face like this, and space-time doesn't have like rocks and ridges and all of that, so it's a perfectly smooth cliff face, this person is going to need some sort of, tether and equipment to find a way to get himself from here out to there. It's really, really hard to climb out something like that. Is if you had this perfectly smooth and almost vertical rock, you're going to need stuff to help you get out of there. Now replace the person with a photon, and it's the same thing. The photon is going to have a tremendously difficult time going out of the black hole. So basically the idea is once this steepness becomes steep enough, once this well becomes steep enough, the walls become like vertical enough, then it's impossible for the photon to get out. It might get really, really close, but it might just, you could consider it the same as a person. If a person is trying to climb out, they might expend all their energy getting up to here. Once they're up here, they're pooped. They just don't have it in them to try and get the rest of the way, and so instead they fall back down into the black hole. So it's the same thing with photons, that they might get close to leaving the black hole, but ultimately the gravitational pull of the black hole drags them back in. And so basically, if these walls are steep enough, there's no escaping. So you could have something like a star that's really, really, really heavy, but this warping of space-time occurs over such a wide area that the steepness of this bending of space isn't really a challenge for the photon. But you could have a black hole that's, the size of Earth, which is on the scale of the universe, that's not very big, and it might have the mass of 10 suns or something, which again on the scale of the universe isn't very big. There are stars that are way more massive than that, but it has such an extreme dip in this region that the walls of this well make it impossible for a photon to get out. You can picture it like if you had a climber in a well with vertical walls, he's kind of stuck there, right? If he doesn't have a ladder, if he doesn't have a rope or a tether or something, he's pretty much stuck there, right? So it's the same thing with a photon. This well doesn't need to be very deep. You could have a person standing in this well, and the well doesn't have to go up, a kilometer. It could be just up to here. But if he can't jump up to that height, then he's stuck there. Now it doesn't matter if it's 5 meters deep or 500 meters deep. One way or the other, he's stuck there, right? So it's kind of the same thing with photons, is that once they're stuck in a well like this, that's it. That's kind of the end of the road for them. They're stuck in this black hole. And so that's sort of a visualization of how this warping of space-time works for stars and planets, the way we were talking earlier, but also for extreme objects like black holes. Neutron stars would be similar, but this steepness wouldn't be as extreme just because they're bigger. You'd have a massive star collapse into a neutron star that might be the size of Earth, but if it collapsed into a black hole, it would be significantly smaller than the Earth. It might be the size of like Manhattan or something. Like it would be the size of like a city, but a large city. And so if you had a neutron star that was the size of Earth, then this steepness, because the object is a little bit larger, this well would widen a little bit, and that makes the slope open up just that much more. Like it makes it a little bit less steep, and it would make it easier for things to escape. So basically, if you had a neutron star that's like right here, then it might still have that steepness to it, and it might still go down as far or nearly as far, but it's just not it's just not as steep, and a photon that's here might be able to get out from there, and a photon that's here might be able to get out from there, but a photon that's in here can't leave the black hole. It's just too steep at that point. And so basically any object can become a black hole if you make it small enough, because if you can compress its mass into a small enough space, that generates this steepness of this well, which causes photons and everything else to get stuck inside that. So basically the speed at which you need to travel to leave this well is called escape velocity. For Earth, it's 11 kilometers per second. So basically, if you have the dip created by Earth, the speed you need to get away from Earth, to get out of that well, is 11 kilometers per second. But for a black hole, the speed you need is faster than the speed of light. So light can't get out, and as far as we know right now, nothing else can travel faster than that. So anything that's in there is stuck, because the speed it needs to leave is impossible to reach. But yeah, so that's just a sort of a brief, simplified, I mean, maybe not that brief, it's been one of our more in-depth videos in some respects, but this has been sort of like an overview of the basics of gravity and how it sort of works on the largest of scales. For a better idea of the visualization, I'd say look up those YouTube videos. This kind of thing is stuff that I've been watching since I was like 6 years old. So it's not like he doesn't explain it in a super complicated physicsy manner. He explains it using pictures and videos and analogies on Earth's surface in a way that people can understand it, which is why I think it's so great. But yeah, look it up. For those of you that didn't enjoy Carl Sagan, I think he speaks in a manner that more people would find interesting compared to Carl Sagan. I find Carl Sagan's interesting, but I do agree that I do understand that some people aren't a fan of the way he talks. So with Brian Greene, he does try and make it at least sound that much more exciting. So hopefully you guys will be able to stay awake through that one, because some of you almost didn't through the Carl Sagan thing. But yeah, so that's sort of a brief overview of gravity, and I figured that would be kind of a nice way to wrap up the year, because my area of expertise is not in biology, chemistry, or geology, so it doesn't really make sense for me to ramble on for half an hour about that. But I figured this would be something that that would interest you guys, and it's something that I've worked with, not extensively, because this is advanced physics. Like when you look at the math of it, it's really hard to understand, but the sort of concept of it is something that I've sort of been working in close proximity with for the last couple of years in some of my courses. So I thought this would be a good way to sort of wrap up the school year. Some of you have had questions about these things, and we just didn't have the time to have a proper discussion on it. So here it is. But yeah, I hope you guys are happy with your science test marks when you get them. I'm not in charge of marking them, so I have no idea how that's going. But I imagine you guys will know today, hopefully. Today would make sense. I was hoping that it would be in time for today's class, but that would be a lot to mark in 1 or 2 nights. So if it's not for today's class, then I'm sure it'll be by the end of this week, so you guys should know that. But yeah, once again, it's been a pleasure being your science teacher this year. I hope you guys have a fantastic summer, and hopefully many of you will be at summer camp, because that sounds like a blast. And for those of you that aren't coming back next year, I'm sure everybody is going to miss you. I know I already miss all of you, so everybody who's there is going to notice your absence next year, but hopefully you guys get the same kind of enjoyable experience from your next school. Hopefully I'll see you guys again sometime soon, but that's it for now.